Metzger, who's a theoretical astrophysicist at Columbia University. Brian received his PhD from UC Berkeley, spent a few years as an Einstein Fellow at Princeton, and then finally joined the faculty at Columbia University in 2013. So, I think over the last few years, we've had a few speakers come and give talks on gravitational waves, but I think Brian's the first from the theoretical simulation community to come and give a colloquium. So, back in 2010, he led a pretty famous study characterizing the optical counterparts of neutron star mergers, where he coined for the first time this term kilonova to describe the optical properties of the events. It turned out that many of these predictions were later verified in 2017 when the first light from neutron star mergers was measured. So, Brian's really one of the leaders in this emerging field of astrophysics. He's won lots of awards already, and I think, just last year alone, he won a New Horizons Breakthrough Prize, as well as the Bruno Rossi Prize from the American Astronomical Society. So we're really looking forward to your talk, Brian, and take it away.
Thank you very much, Jeremy. It's a pleasure to be here remotely. I wish I could be there in person, but that's the nature of our times right now. So yeah, I'm very excited to talk to you today about some of the physics of neutron star mergers. We've only had one event where we have detected electromagnetic light from it. So I'm going to focus on that event, even though it is a few years old, and even though I'm sure with Alessandra and other people locally, you've heard quite a bit about this event. But then I hope to sort of broaden it a little bit to describe where we're going in this field, some of the diversity of electromagnetic signatures we may see from these gravitational wave events, and how that can shed light on a number of important topics, such as the origin of the heaviest elements in our universe, the equation of state of neutron stars, what's a neutron star made of, densities above nuclear saturation density, and try to give you a little bit of the lay of the land. But we have to get there first, so let me get started. Oops, okay, now I can advance my slide. So when I was in graduate school, this is sort of, if you opened up a textbook, this is where it would tell you the origins of the elements, where the elements came from. And this is, of course, one of the goals of nuclear astrophysics, is to identify when and where the periodic table was forged. Hydrogen and helium were largely created during the Big Bang that gave birth to our universe. The lighter intermediate mass elements, the elements of life, we think were largely formed in massive stars and then expelled into space when those stars explode as supernova. So this is, for instance, Cassiopeia A, a supernova remnant that exploded about 350 years ago. It's a bit controversial, but it may have been the last galactic naked eye supernova, one that you could see, if you went outside at the right part of the world at the right time. And the original star that gave rise to what you see was about 17 times the mass of our sun. What you're seeing here are hot, you're seeing X-rays from Chandra's X-ray Observatory produced by this hot debris from the explosion as it's running into the interstellar medium of gas. And by this time, 350 years later, it's about 5 light years across. But by analyzing the colors of these X-rays, the energies of these individual X-rays, you can ascertain the specific production of these elements of life I just mentioned. Silicon is one type of X-ray emission, sulfur, calcium, iron. And so this is sort of our empirical basis for the famous Carl Sagan quote that the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interior of collapsing stars. We are made of star stuff. This is the proof. We can see it directly. We have lots of evidence for where the top of the periodic table comes from these massive stars. And those are the most common elements in our universe. But as you get to the bottom of the periodic table, the heavier elements, heavier than iron in particular, there's a lot less certainty as to where these come from, particularly about half of these elements. Their origin is largely unknown. But nevertheless, these include the precious metals like gold, silver, and platinum, and the transuranic elements, uranium and plutonium and thorium. Obviously, our society would be very different if these elements existed on Earth in different abundances than they actually do. So it would be nice to know, where these elements are coming from, despite all of their important applications to our day-to-day lives. So this is actually an old problem of how we can make iron in stars, but how you turn iron into gold is, of course, the dream of an alchemist in the Middle Ages. And it's not so easy. Iron is roughly equal numbers of protons and neutrons, and a gold nucleus has many more of both, but is particularly rich in neutrons. You can't form gold inside a star because if you have to get really hot to overcome the Coulomb barrier of increasingly heavy nuclei. And once you get so hot, it's just energetically favorable to dissociate the nuclei, not to build them into heavier ones. But in principle, you can still turn iron into gold. What you have to do is bombard an iron nucleus at a very high rate with neutrons, because they can overcome the Coulomb barrier. They can build up a heavy radioactive isotope. And particularly if you capture them at a very high rate. This is known as the rapid neutron capture process. But then the question shifts. Okay, I can turn iron into gold if I have a high enough density of neutrons. Where do I find a high density of neutrons? Neutrons are unstable. They decay in free space into protons in about 10 minutes. So where do I find neutrons in enough abundance to turn iron into gold? Well, the obvious answer is a neutron star. This is a star almost entirely made of neutrons, at least in its outer layers. This is showing you again the picture of the Cassiopeia remnant, and this point source in the middle. This hot dot is a source of very hot X-rays produced by this cooling neutron star. And neutrons are stable inside of a neutron star because it's so dense that the Fermi sea is full, so that blocks the beta decays of the neutrons. But nevertheless, we don't actually know what's inside of we have lots of observations of neutron stars. They definitely exist in nature, but we don't know a number of their properties particularly well. We don't know what is the equation of state of matter as you get above nuclear densities, which is what you get inside of a neutron star. We don't know if it's entirely a hadronic material, if there's a phase transition to deconfined quarks. Different equations of state predict different relationships between the mass and radii of neutron stars. But at present, there are some exceptions. We're getting better at measuring radii, but largely we can't yet distinguish whether the neutron star has a radius of, say, 11 kilometers or 14, and this would have a big impact on what are the properties of matter. Another property we can measure potentially for a given equation of state is each one predicts a maximum mass that could stably support a neutron star, above which it would collapse into a black hole. And so if we measure the masses of a bunch of neutron stars, we know that the equation of state must support at least a mass, equal to the largest of those masses we measure. And the current record holder is about 2.1 times the mass of our sun. So we know that the maximum mass the equation of state can support is at least 2.1 solar masses, but we don't know how much higher. But obviously, these properties are going to affect what happens when you have a merger of two neutron stars. If you don't know what their sizes are or what their masses, maximum masses are, that can be problematic. These neutron stars, so you have neutrons in a neutron star. How do you get them out? Well, you have to slam them together at close to the speed of light, and nature does this naturally, because if you put two of these stars into a tight binary, it's a strong source of gravitational wave radiation. Of course, the most famous example probably is in our own galaxy is the Hulse-Taylor binary pulsar, where over the course of several decades, people were able to measure the orbital period very accurately by timing the arrival of the pulses from the pulsar, and they were actually able to see the orbital period shrinking due to the loss of energy through gravitational waves. And as the two stars approach one another, they orbit faster and faster. So this produces higher and higher frequency gravitational waves, and also the strength of the interaction becomes stronger. So the waves get stronger in power. So if you could hear it audially, this would sound like a chirp, something increasing in frequency and amplitude. And so the great thing is that with the LIGO detectors and Virgo detector in Italy, we now have the ability to, we don't, but I don't, but they have the ability to detect these gravitational waves directly. I'm not going to go into how they do that. It's amazing. But they discovered their first neutron star merger, as you're aware, in August of 2017. We call it GW 170817 based on that discovery date. This is showing you the gravitational wave track that they detected. Through the gravitational wave emission, LIGO is able to constrain the masses of the incoming stars. They're not able to measure the individual masses particularly well, but what they are able to measure surprisingly well is the total mass of the ingoing binary. And in the case of LIGO's first neutron star merger, it was about 2.74 times the mass of our sun. And this is actually smack dab. If you look at the galactic binary neutron stars that we know of, this is sort of smack dab in the middle of that population. So it was sort of not too surprising that we saw this type of merging neutron star as the first one. It was surprising how close this event was, which I'll come to in a second. So after the discovery of gravitational waves, you'd like to know where they're coming from on the sky so you could see if there was any type of electromagnetic signal coming from them. And so the way they do this is essentially through triangulation. It's more complicated than that, but essentially the gravitational waves arrive at a slightly different time in Louisiana versus Washington, where the two LIGO detectors are located, versus in Italy. And so you can use that information to pinpoint where they're coming from. In the case of this first neutron star merger, it was coming from the constellation of Hydra, which at the time was, I believe, over the Indian Ocean. So this launched a worldwide campaign of electromagnetic follow-up within a few hours. The coordinates were disseminated to astronomers who pointed their telescopes both on the Earth and in space, both optical and radio and X-ray and gamma ray telescopes. And so I'm going to go briefly over what happened during those first 11 hours of the discovery here. You've no doubt heard this story before. So the first thing that happened is within 2 seconds of the end of the in-spiral, there was a burst of gamma rays detected by NASA's Fermi Gamma Ray satellite. It was also detected by the European Space Agency's Integral satellite. So at that point, you knew it was coming from this part of the sky. Then the two LIGO detectors, the North American gravitational wave observatories, localized it to this patch. Then Virgo, the Italian detector, which actually didn't see the signal, nevertheless was able to help localize it further. There were a handful of galaxies within this air region, and several of the groups sort of dutifully probed each of these galaxies and found the fading counterpart in this host galaxy, NGC 4993, at a distance of only 40 megaparsecs. So this was surprisingly close, given that I think LIGO could have detected one to roughly twice that distance. So it's a little bit surprising they detected the first one in our backyard effectively. So what did they see? Well, they got on 11 hours, a half a day after the discovery, and over the course of the ensuing week, they saw a fading optical infrared glow. We discover, as you know, since there are many people who work on supernova observations, we discover supernova all the time. They rise and fall on a timescale of weeks. This was fading much faster than an ordinary supernova. It was unlike any stellar explosion that had been seen before. And the story I want to tell you is essentially how we understood what we were seeing essentially from the discovery of this, and how it's the first time that we have evidence for the formation of these heaviest elements in the periodic table. But to do that, I have to explain some of the diversity, what happens when two neutron stars merge. So it's going to turn out that the outcome of the merger, and there are multiple outcomes, depends sensitively on two things. One is the ingoing mass of the binary, and the other is this maximum mass that the equation of state of a neutron star can support, the TOV mass, Tolman-Oppenheimer-Volkov mass. So it could take the two stars a long time to merge their gravitational waves, possibly of order the age of the whole universe, but the final few orbits are occurring on a timescale less than a millisecond. You have the coalescence of the two stars. It turns out that if the total mass of the binary exceeds about 30 to 60% of the maximum mass of a single not rotating neutron star, the outcome of the simulation, and this is based on numerical relativity simulations, is a prompt collapse of the remnant to a black hole, immediate collapse. But what happens more frequently for less massive neutron stars is that the merger doesn't immediately collapse into a black hole. Instead, it forms what we refer to as a hypermassive neutron star remnant. This is an object which is temporarily supported from collapsing by its rapid and differential rotation. It's essentially held up by centrifugal forces. But on some time scale, there is viscosity in this object, which is probably of a turbulent hydrodynamical or magnetohydrodynamical flavor, causes a redistribution of angular momentum in this object, taking it from a differentially rotating object into a solid body one. And that process of redistributing angular momentum destabilizes the object, and so it collapses into a black hole. But unlike this case, it takes a little bit of time. It may take up to 100 milliseconds or maybe even longer for this redistribution of angular momentum. But in this case, unlike this case, you end up producing a fairly massive torus around the black hole because it has to shed angular momentum to collapse. And in that process, you generate a pretty massive disk of material around it. It's even possible if the mass of the ingoing binary is sufficiently small, less than about 20% above the maximum mass. Even once this differential rotation has been smoothed out, even once the star is in a solid body state, which is the minimum energy configuration for a fixed angular momentum, it still is stable. It still does not want to collapse into a black hole. It has to actually globally lose angular momentum. It has to actually spin down to collapse into a black hole in this case. And this could take much longer. If its magnetic dipole spin down and the star is, has a strong magnetic field, it could take a few minutes, it could take hours, it could take days. So you have disparate outcomes of this event, this merger event, that just changing the ingoing mass by tens of 20% can possibly produce qualitatively distinct outcomes. And what I'm going to argue, and what I think is the overall picture, is that LIGO and Virgo can tell us what is going in. They can measure the total mass reasonably well. And then electromagnetically, with our telescopes, we try to figure out what are these outcomes, and is this the right picture? And if it's not, what's going on? And so this is the story I want to tell you. And what I'm going to get to eventually is that I think 170817 likely went through a hypermassive neutron star phase. It did form a black hole, but not immediately. And I'll try to get to the evidence that that was the case. So I'm going to show you a numerical simulation of two merging neutron stars. This is from David Radice and collaborators. You're going to see this is hydrodynamics, including general relativity. You're seeing the final few stages of the in-spiral. The two stars will start to tidally distort one another. There will be some mass ejection out of the outer Lagrange points of the binary. The coalescence into a single star, it becomes a shock-heated object. There's a cloud of debris, which is sent out in a fairly spherical fashion. But then there's this disk of material surrounding this hypermassive star, which ultimately loses enough angular momentum to collapse into a black hole. And so this is the qualitative picture of how the merger occurs. So what types of electromagnetic emission do we actually expect from these mergers? Well, it's likely to be a sensitive function of our viewing angle with respect to the binary axis. The idea has been around since the 1980s that these systems would produce accretion disks around black holes, and that the accretion of this material onto the black hole would power a transient jet of relativistic plasma. And that relativistic plasma, through some form of dissipation we don't completely understand, would produce gamma rays. But those gamma rays would be tightly beamed along the angle of the jet. And in fact, as I mentioned, we did in fact detect a burst of gamma rays following this event. Even though we were, so we think based on observations of cosmological gamma ray bursts, where we see things we think are mergers but are too far away for LIGO to detect, we think the opening angle of these jets is about, of these gamma ray bursts is about 10 degrees. For this event, we were observing it about 20 or 25 degrees off of the jet axis, but we still saw a burst of gamma rays. It was just a lot dimmer than the ones we've seen cosmologically, where we're probably looking down the barrel of the jet. But there were a few mysterious properties of this burst of gamma rays. I don't want to go into this in great detail, but I'll mention one, which is that the gamma rays were delayed by about 2 seconds, the arrival of the gamma rays after the end of the two stars had collided. There are various reasons for why you would expect an intrinsic delay, other than making the speed of light different than for gravitational waves and light. One is it could have taken, it's thought that maybe the jet that made the gamma ray burst requires the formation of a black hole. It could have taken 2 seconds in principle to make the black hole. The black hole could have formed and the jet could have formed right away, but it may have taken 2 seconds for the jet to get out of this cloud of debris, which is itself moving out almost at the speed of light. That's my favorite explanation, that it probably is the jet getting out of this cloud. But we don't know, and it's a very interesting physics question. It could also, in principle, could also be that there's a slight difference in the wave speed of gravitational waves in light, although that's quite speculative. But this burst, as I mentioned, was substantially less luminous than gamma ray bursts we have seen at cosmological distances. This is not too surprising because we weren't in the barrel of the jet axis, but we nevertheless know that this event did produce a very powerful jet, which is similar to those we've seen at cosmological distances, not from the gamma rays, but from the fact that after about a week or so, we saw a delayed X-ray and radio emission coming from this jet as it slammed into the interstellar medium. This is what Alessandra worked on quite extensively, was showing that that we actually do have evidence that there was a more powerful jet out of our line of sight, so-called orphan afterglow from the jet. And so we do think this event produced a powerful jet, similar to those we've seen from cosmological gamma ray bursts. But the broader story I want to talk about in this talk is not the relativistic jet or the gamma rays, but the more isotropic emission, which comes from material which is flung out at sub-relativistic speeds. And you could even, in principle, see this if you were looking at it in the equatorial plane of the binary, and this is known as the kilonova. So the basic point of the kilonova is that there are several sources of neutron-rich ejecta at different stages in time after the merger. So I showed you the simulation showing this tidal material that's ejected in the equatorial plane of the binary. When the stars collide together, there's a sort of shock-heated cloud of debris. We refer to this as dynamical because it comes out quickly on the dynamical time, but there isn't a whole lot of it. Most simulations find about 1,000th of a solar mass coming out dynamically. It has a high velocity and it comes out very quickly. But the more important dominant source of mass ejection is not what you see coming out of these merger simulations, but actually over longer periods of time from the accretion disk, the one that's feeding the black hole, that's powering the gamma ray burst jet. As I'll show you in the next slide, this produces quite a bit, outflows from this accretion disk produce quite a bit more mass, up to even 1/10 of a solar mass, but it comes out over a period of seconds, and so it can't be followed in the same simulations that people use to follow the merger itself. And it tends to come out with a little bit of a lower velocity. And the thing I want to talk about later in my talk is the fact that the composition of these outflows from the accretion disk is very sensitive to the lifetime of the neutron star after the merger, before it forms a black hole. And this is because the neutron stars in these systems, when two stars slam together, they're extremely hot. So they're a very powerful source of neutrinos, which irradiate the accretion disk and all of its winds. And neutrinos can turn neutrons back into protons. So even though these disks are very neutron rich, their composition, they will not be as neutron rich, it turns out, due to these neutrino interactions, if the neutron star is surviving a long time after the merger. So as I mentioned, in this context, black holes are fussy eaters. Here I'm showing you a numerical simulation of the magnetorotational instability and accretion disk onto a black hole following a neutron star merger. This was done by Daniel Siegel, who's now at Perimeter Institute. And so we did these simulations. We were trying to quantify how much of the accretion disk makes it into the hole, how much is ejected in outflows. We include neutrino cooling. It turns out that these disks are so dense that they can actually be cooled by neutrinos efficiently in the equatorial plane of the disk. But the upper layers of the disk cannot cool effectively because the temperatures are not high enough to activate the neutrino cooling. And so the upper layers get heated by MHD reconnection, and this ends up driving a thermally driven outflow that kicks away a lot of the mass and prevents it from getting into the black hole. And so we find that about 30% of the torus mass that you plop down ends up getting ejected in winds with a velocity of about 1/10 the speed of light. So if your torus is about 1/10 of a solar mass, which is pretty typical in simulations, you expect several hundredths of a solar mass to be ejected by these winds. And it's probably more a dominant source than the dynamical material. So whatever your source of ejection, whether it's a dynamical or a disk wind, you're ejecting very hot, dense, neutron-rich material into space. And as it decompresses, this provides a site for rapid neutron capture nucleosynthesis, what I mentioned back with the alchemist slide, where where you form these heavy pseudonuclei like iron, but then they're embedded in this very neutron-rich sea, and so they're able to capture neutrons over the course of about a second after they're ejected and form these heavy elements directly in the material being ejected. So here I'm showing you our process nuclear reaction network. This is proton number on this axis. This is neutron number. The colors show you the amount of those isotopes present. And we're following a single fluid element as it decompresses from very high temperatures and high density. So these two bars will go down, indicating we're decompressing. And on the top, you have a running distribution of what nuclei are formed. So this is the abundance versus atomic mass number. So what happens first is your neutrons get together with some of your protons, your protons get together with some of your neutrons and form these heavy pseudonuclei, which form an island around here, around a little bit above the iron group. But then you capture neutrons, which moves you this way, and you undergo beta decays, which moves you up this way. And so as I let the simulation run, you will see in this way that I'm able to form extremely heavy isotopes by capturing neutrons. And I keep capturing them until about a second when I run out of them, and then everything slowly decays back to the stable valley of the nuclei, which are here over a time scale of weeks, of months, of years, et cetera, et cetera. So at the end of the day, if you have enough neutrons, you end up producing an abundance pattern, which looks qualitatively similar to the solar system pattern of these elements. So the simulation I just showed you, which was just a single fluid element making a number of assumptions about the nuclear cross sections, not all of which are understood. But nevertheless, you get qualitatively the second and third peak, which are set by closed nuclear shells. And this is, the peak where xenon and silver reside, or the platinum and gold peak, or the transuranic elements. So if you have enough neutrons, you can produce qualitatively the sort of abundance patterns you would see on the sun. But the important point for the kilonova is that these isotopes you produce are not only heavy, but they're radioactive. So they continue to heat the matter that's been expelled from the merger long after these elements are formed. And this radioactive heating is what powers the bright light that we see. So in 2010, we did the first calculations of this radioactive heating as a function of time after the merger. If you have a single decaying isotope, you'd have a constant heating followed by an exponential decay. But here you have hundreds of isotopes. So one decays with a short half-life, decays into one with a longer half-life, which decays into a more stable one with a longer half-life. And when you add them in aggregate, you get a power law heating, which is going something like T to the minus 1.3. And so this power law behavior was first pointed out by Leon Paczynski in 1998. But prior to our work, no one had actually calculated this heating. And so these Leon Paczynski models, while very prescient, we're not making predictions for how bright this emission could be because they didn't know the overall normalization of this heating. And that's what we calculated but first in 2010. But what matters is not what heating is happening very early after the merger, but rather what is the heating that's happening on timescales of hours and days and weeks, because this is when the ejecta is finally becoming transparent, so where all the heat you're releasing can actually get out to an observer. So this is what we were really focusing on, is what is the heating on a timescale of about a day, because that's the observable window. And so as this debris cloud expands into space, initially the photons from this heat are trapped, but then once, as I mentioned, it expands enough, the light is able to get out. So we did the first calculations of these radiative transfer calculations following the escape of heat from these events in 2010, which included this physical heating. And what we found is that the luminosity would peak at a few by 10 to the 41 ergs per second, maybe 10 to the 42 ergs per second on a timescale of about a day. That's when the ejecta is becoming transparent, and thereafter it would follow the radioactive heating. So this was about 1,000 times brighter than an event we call a nova in our galaxy. And so we call these events kilonova, and that name has largely stuck. Some people prefer macronova for various reasons I don't understand. But kilonova, kilonova is the term we use. It probably, in retrospect, should have been called an R nova because it's really powered by radioactive decay of R process nuclei, or maybe a radioactive decay nova, because that's essentially what you're doing, is you're creating a bunch of radioactive debris and expelling it into space and seeing the residual heat released as it decays. So following 17817, as I mentioned, we saw this fading glow of light. And in the first week, I asked the observers to send me the light curve, and I just literally overplot our first model in our paper, and it actually worked amazingly well, fitting this event. And so I knew immediately that we were seeing an R-process powered transient, and the first time in nature that people had seen the direct creation of these elements. And this, of course, is an old mystery going back to Burbage, Hoyle, and Fowler, and Al Cameron in the 50s, where they laid out all of the different physical processes that could give rise to the elements. And since their discovery, since their paper, astronomers have kind of identified where in nature all these different nuclear processes are happening, except for the R process. That was the last one. So you can ask the question, are neutron star mergers the dominant source of the R process? Is most of the platinum on my wedding band coming from neutron star merger? So at what rate these elements would need to be created in our galaxy prior to the formation of the sun to seed the Earth with enough gold. And now, thanks to LIGO, we know roughly what the rate of neutron star mergers in the universe is, and also probably in our own Milky Way type galaxy. So you can, even though it's highly uncertain, both of these quantities, each merger would need to produce about 1/100th of a solar mass in order to explain all of the R process on the Earth. And this single event, as I'll show you in a second, we think produced several hundredths of a solar mass. So it seems likely that a significant fraction of the heaviest elements on the Earth come from these mergers, although I can't yet tell you whether it's 10% or 99%. We just don't have the statistics with one event. But I think it's clear that these are an important source. And if you think this event produced the solar distribution of our process nuclei, which is highly debated, it would have produced about 10 times, the single event would have produced about 10 times the Earth's mass in gold, and 50 times the Earth's mass in platinum. So it's quite a prodigious event. These are rare events, but they're very prodigious, and the rates seem to work out. But there's more than just the bolometric light curve, the luminosity you would need to explain these events. You also need to understand their colors. And this event that we observed started off very blue for the first few days, and then it became very red. So it started off in the ultraviolet and optical, and then it moved to the near infrared very quickly. And it turns out, so what is that telling us? What are the colors of this kilonova telling us? And there's also spectral information about this. It's telling us about the composition of the ejecta. So Dan Kaysen and Jenny Barnes pointed out that, well, first off, what is preventing the photons from diffusing out of this ejecta? It's a sea of atomic absorption lines. And it turns out that the opacity in the optical and UV is very sensitive to the density of lines, how many lines per unit wavelength. Light elements, light R process elements like iron and the lighter R process elements, they have a fairly simple, relatively speaking, valence electron structure, which doesn't have an enormous density of lines. They have a lot of lines, but still a lot, but not enormous. The bottom of the periodic table, the lanthanide and actinides are much more complex, atomically speaking. They have F-shell valence electrons. They have a much higher density of atomic lines. And as a result, they have a much higher optical and ultraviolet opacity. And so if you have a kilonova that just produces the lighter R process elements, the prediction is what I showed you. It would be a blue event that peaks about a day after the event. However, if you have these heavier elements, it takes longer for the light to get out. It's cooler when it does get out. You predict an event that's peaking in the near infrared on a time scale of about a week. So what we saw with this event was both. We saw something that was very blue, and it became very red over the course of a week. This was also anticipated because you can see different light from different components of the ejecta. In particular, if you have, say, a polar outflow that has relatively few neutrons, it would only be able to create these lighter elements, and you would expect low opacity and blue emission from it. And if you had a more spherical or equatorial outflow that had a higher abundance of neutrons and was able to capture its way up to these heavier elements, then that would produce a redder infrared emission. And for an observer out here, you could actually, at least if you're observing it in the polar region, you could see both. That's what we pointed out with Rodrigo Fernandez in 2014. And that seems to be what we see. In fact, I originally had a question mark next to the blue because we weren't sure if the red stuff would block the blue stuff's emission. It turns out it doesn't. And so this is how most groups have actually modeled this event, is with two separate components, a blue component and a red component. And when they're able to get reasonable fits to the photometric observations, this is astronomers' units for brightness, magnitudes versus time. Ignore this, just this is 2 weeks. And you see, the event was fading very rapidly in the blue bands and more pronounced in the infrared bands. And if you fit it this way, you need about 1/100th of a solar mass of the LIDAR process stuff expanding at a high speed of about 0.3 C, and about 3 or 4 times as much of the red stuff with the heavier elements expanding at a lower velocity. So where does this come from in the merger? Well, as I emphasized, the dynamical ejecta, what you see coming out, during the early phase of the merger, isn't a whole lot of mass. Here I've compiled the ejecta velocity and dynamical ejecta from a whole suite of numerical simulations. There are all these points. And then here is the observations from 170817 of the blue and the red component. What you see is it's possible that the dynamical ejecta could contribute some of the blue kilonova. It's hard pressed to explain either the velocity or the quantity of the bulk of the ejecta we saw, the red kilonova. But this is naturally explained as coming from the accretion disk, what I showed you earlier, which produces quite a bit more mass with a lower velocity of about 0.1 C. So I'm convinced that most of the ejecta we saw from 170817 was not of a dynamical form, but rather coming out over a longer period of time from the black hole accretion disk. You can also probe with the kilonova the time scale it took the neutron star remnant to collapse into a black hole. And this is because, as I mentioned, while the remnant after the merger is still surviving, it's very hot. It's a strong source of neutrinos, 10 to the 53 ergs per second in neutrinos. And those neutrinos are irradiating the disk and its outflows. And so we did this exercise back in 2014 of taking a neutron star light bulb of neutrinos and collapsing it to a black hole at various points in time and quantifying the composition of the ejected winds. And what we found is if the black hole forms quickly, most of the ejected material is very neutron rich and you would get a red kilonova from the disk winds. But if the neutron star survives longer and longer, it basically, the neutrinos turn the neutrons back into protons. And at some point, you don't have enough neutrons to make these heavy elements anymore. When the remnant is surviving for longer than, say, a few hundred milliseconds, you just don't get much in the way of the heaviest R process being produced. This is showing it. We then worked with Dan Kaysen to actually make light curves of this. This is showing the same thing. Collapse right away, collapse a little later. If you collapse right away, you're dominated by the infrared part. If you collapse later, you become dominated more by the bluer part. And so the fact, and if you keep having it survive for a longer than 100 milliseconds, you basically kill the red part altogether. So I would argue that the fact that we saw evidence for these lanthanides of a red component to the kilonova in 170817 disfavors an extremely long-lived remnant, and therefore indirectly favors a black hole forming eventually in the system. So let's go back to this diagram showing the different outcomes of a neutron star merger. And now I'm going to make the case that we saw from 17817 was this one. So we can rule out a prompt collapse because there's just too much mass ejected overall from the kilonova. You never get a massive disk or a lot of dynamical ejecta when you have a prompt collapse. So we can rule that out. You can also, I think, rule out a very long-lived remnant. There are various lines of argument along this, some more debated than others. I would say the kilonova was too red. Other people have said we wouldn't have expected to see a GRB if a black hole didn't form. I think that's more contentious because I I don't know for sure that you need a black hole to make a GRB. I think it's probable you do, but we can talk about that. And I'll come to a third one in a second, which is that the kinetic energy of the kilonova ejecta was lower than I would expect if we had a long-lived remnant. So by elimination, and also by our prior, which was that this was the most likely outcome, given what we a priori knew about the equation of state. To me, this was the most likely outcome, was a hypermassive neutron star that did collapse into a black hole within at least tens to hundreds of milliseconds. So let's return back to our equation of state figure. So again, one of the goals is to try to constrain the equation of state. You know, if this orange line were the right equation of state, then it would predict a 2.2 radius kilometer, sorry, a 12.4 kilometer radius neutron star, and with a maximum mass of about 2.4. So can we use our observations, and that's probably not the right equation of state, but can we use our observations of this merger to constrain these? So what you can do is, because you've ruled out a prompt collapse, it turns out that the prompt collapse threshold, whether it's 30 or 60% above the maximum mass, depends on the compactness of the neutron star. And so Andy Basvine and collaborators, and Radice to some extent, have used the no collapse threshold to put a lower limit on the neutron star radius. The thing I want to emphasize is that LIGO, again, measures the total mass of the binary. So we know we know m tot, and we're trying to infer some combination of the maximum mass and the radius. And it turns out that this combination is also sensitive to radius. So you can put a lower limit on the radius. On the other hand, if you can rule out a supermassive neutron star remnant, for reasons I mentioned, then you're able to put an upper limit on the maximum TOV mass. In other words, if the TOV mass were higher, given this ingoing mass, we would have expected the object to survive longer, and we don't think it did. So you could take these constraints and put them, all the constraints that people have claimed from this event, not all of them, but a good fraction of them, on a qualitative diagram. This is not meant to be precise, but it's quite striking. I didn't mention it, but LIGO is able, through the gravitational waves alone, Jeremy's worked on this, to put an upper limit on the radii, or the tidal deformability of neutron stars, from not seeing a signal in the gravitational waveform of a finite neutron star size. And that works out to be an upper limit of about 13.5 kilometers. And what I'm saying is it's model dependent, but people have put lower limits on the radius based on not collapsing to a black hole immediately. And then with my student Ben, and followed up by other groups, we argue there's an upper limit on the TOV mass by not producing a long-lived remnant. And so we're honing in on a gravitational wave motivated constraints on the equation of state. They're all subject to systematic uncertainties. But this is quite exciting to me because this is truly multi-messenger science. I think sometimes multi-messenger is a buzzword, is a sort of just thrown around. But here we're really using gravitational wave data on the total mass, and we're using electromagnetic observations to infer an outcome and putting them together to get more than you could get with either individually. So this is very exciting. And we want to do this for more events to see if a self-consistent picture is holding up. So the future in this field is bright and loud. We expect more mergers. I'll come to one that was discovered in 2003 in a second. LIGO's 2004 run is scheduled to start in a little over a year, maybe a year and a half. Alessandra knows. We expect to detect similar events to 170817, same type of ingoing binaries, maybe observed from a different angle. We expect, hopefully, to find different ingoing masses for the two neutron stars, a higher mass or a lower mass system. LIGO hopes to detect, black hole neutron star mergers that may have seen one already. And those could accompany, have or may not have electromagnetic counterparts. There it depends on whether the neutron star is swallowed whole by the black hole or whether it's tidally disrupted before being swallowed whole. But if the neutron star is tidally disrupted before falling into the horizon, then you can get many of the same qualitative signatures I talked about, maybe a disk, a GRB, maybe a kilonova. And so in addition to the two LIGO detectors, what's enabling these advances is, of course, LIGO's 04, eventually upgrade to A+, and then they're adding a detector in India middle of this decade, hopefully, and then the Japanese have their own detectors. So there's going to be a worldwide, network of these detectors, along with telescopes on the ground in space, which enable this type of program in the next decade. So as I mentioned, one thing we may look for are events viewed from different angles. If there is high opacity material in the equator from a tidal tail, it could potentially block some of the blue emission, depending on how slow or fast it is. So we may see events which are redder because of this geometric effect, because the red stuff has this high optical opacity, so it can block the blue stuff, whereas the blue stuff can't block the red stuff. So that would be quite interesting if we saw the same chirp mass as 170817, but from a different angle and it looked different. That would be pretty cool. We may be able to see more massive ingoing neutron star binaries that collapse to black holes immediately. The prediction is, in this case, that you would have less ejection of material overall and less neutrino irradiation because there's no long-lived neutron star. So I would predict that the kilonova would be dimmer and redder than we saw from 170817. We had a potential chance to test this with LIGO's second neutron star merger, which occurred last year. The exciting thing about this event, 190425, was that the total mass of the binary was around above 3.2 solar masses or so. The first merger, as I mentioned, was smack dab in the middle of the distribution of masses of double neutron stars in our galaxy, whereas the second one was substantially higher. We don't know why. We don't know. Presumably it was formed in a different way than the double neutron star systems in our galaxy. But unfortunately, we could not search effectively for a kilonova from this event because only one LIGO detector was operating at full sensitivity. And so the sky error regions through this triangulation process were much poorer. It was only localized to thousands of square degrees on the sky. And it's much harder to find a needle in a haystack, to find a dim, fading transient when you're trying to search a major chunk of the sky than if they give you this nice 30 square degree region that they had for 170817. So there was no counterpart found, but this is not surprising because they couldn't search this whole region to the necessary depths. What I'd also hope to see is a low mass ingoing binary that doesn't collapse to a black hole so quickly, but instead produces a long-lived object. Numerical simulations show that during this process, there is so much shear energy liberated that the magnetic field inside the star is amplified to an enormously high value, higher than 10 to the 16 Gauss. We don't know that will come out as a dipole magnetic field, but it seems likely the object will have a dipole magnetic field. So now you've created a star which is not only spinning at breakup, but has the strong, a magnetic field which is as strong as neutron stars we call magnetars in our galaxy. So you've created a millisecond magnetar, and depending on how long that could survive, that could produce a very different signal than you would get from a black hole. I already mentioned that if the neutron star survives for a long period of time, it will zap the outflows with neutrinos and turn the kilonova blue. But another thing that could happen is you could get a long-lived high energy emission from this magnetar. It could also boost the energy of the kilonova. And so the basic point is when you have a merger and you form a black hole, you're essentially trapping the spin energy of the system that you haven't radiated away in gravitational waves. You're essentially trapping that in the black hole, where it, for the most part, is stuck. But when you merge and you form an object which is stable, then it actually has to lose that rotational energy to form a black hole. So there's a sort of potential gain you have to overcome. And if you lose that energy through magnetic dipole spin down, then it has to go somewhere. It's going to go into your environment. And the rotational energy that one of these remnants contains is about 10 to the 52 or 53 ergs. So if you could extract that energy and pump it into a jet or into the kilonova ejecta, you would radically alter the signature. The luminosity of the spin down could greatly exceed the radioactive power. It may be a much brighter event. It's probably a faster evolving event. It could look qualitatively different. Some of this could be lost still in gravitational waves, however. So we don't really know it's going to release as much energy. But I should say in 17817, the total energy that came out in the jet of the kilonova and the GRB was only about 10 to the 51 ergs, whereas with these long-lived remnants, you could have orders of magnitude more energy potentially available. So it would be very exciting to actually see a low mass binary that might produce a very stable remnant. You could also hope to find gravitational waves, as Alessandro has worked on from this post-merger object. So my final slide is just to say I'm essentially proposing a kind of Vogt-Russell theorem for binary mergers. If you don't know the Vogt-Russell theorem, it's basically that mass is destiny for stars. If you tell me the mass of a star, I can uniquely ascertain its evolution. And I'm arguing that I think binary mass is essentially the same kind of thing. It's true that with different mass ratio binaries, there are different tidal ejections, but I don't think the tidal ejecta is the dominant form of ejecta. So I actually don't think mass ratio matters as much as total mass of the binary. The kilonova ejecta and the GRB jet, I think, are going to depend sensitively on the stability of the remnant. And that depends on the total mass relative to the TOV mass. So one predicts abrupt qualitative changes in electromagnetic signature as I pump up the mass of the system. As I mentioned, a high mass system will prompt collapse, lower mass hypermassive neutron star, lower mass supermassive neutron star, and potentially sufficiently low mass binary might produce a neutron star that never forms a black hole. So as we observe systems, what I'm hopeful is that we will be able to put them in these different categories and use that both to learn something about the equation of state and also possibly add more precision to our electromagnetic follow-up. For instance, LIGO can actually measure the chirp mass very quickly. They could actually get it, I think, to a few percent. There's some papers that have shown they could get it to a few percent accuracy within minutes after the merger. So if they measured a very high mass binary, they might tell the astronomers, this is a prompt collapse system. You're probably going to have to go deeper with your telescope to find it. Or this is a low mass system. It produces a long-lived object. You smaller telescopes, you may still detect something because it could be really bright. This system, all the maybe the first 10 mergers will all have the same. Well, they don't all have the same mass as 1797, but maybe they'll all, 9 of the first 10 will be similar, and you'll want to know that the 11th is different somehow. So I'm advocating that LIGO release more information to help fill out this chart. And I think that's certainly possible in a way that would preserve the integrity of their data for the collaboration. So it's stated another way, we want to fill out a matrix which connects a gravitational wave axis to an electromagnetic one. We only have one event, but as we fill this in, I'm hoping that we can converge on a complete picture of this. And maybe we'll be completely wrong. Maybe all of these categories will not conform to reality. And that will tell us our numerical simulations are missing some important physics. Maybe they're not including a first order phase transition in the equation of state, which affects the boundaries here. Or maybe there's some additional dependencies entering the system. Okay, so this is what I'm excited is. This is the expectation that we're going to have these different systems. If we don't see this, I think that's where we're going to learn something. We're going to learn something either way, but I think it's very exciting. So in summary, with the first neutron star merger, we had a surprisingly well-behaved event. This was a figure I made in a review with Rodrigo Fernandez in 2016. So event, signal, phase. So the first phase, you have the 2 neutron stars in spiraling. They produce a gravitational wave chirp. It may be accompanied by a precursor. I didn't have time to talk about this, but there may be a fast radio burst type precursor during this phase. The 2 stars collide. They form a remnant. If the star mass is high, it will quickly form a black hole, possibly producing a GRB. If it's a lower mass system, it may produce a neutron star that survives a long period of time and produces some extended X-ray emission. The ejected material during this process, either through dynamical or disk winds, will undergo the ARP process about a second after it's ejected. And as this material decays, it can produce a range of different thermal transients I've called kilonova here. A blue one from the lighter R process elements, a red one from the heavier ones. And then whatever is left goes running into interstellar medium and produces a shock wave, which produces a radio synchrotron emission, also from the GRB jet. which I didn't have time to discuss. So you can ask which of these signals we saw from 170817, which we were able to rule out, and which we hope to see in the future. Well, we saw gravitational waves, we saw a GRB, we saw a blue and a red kilonova, we saw radio emission, although we haven't yet seen the radio emission from the kilonova, we've seen it from the GRB jet. We don't know, we did not see, well, there's some controversy here, but I don't think we saw clear evidence for late time X-ray emission, very clear evidence, I would say. There's some claims there may have been a flare, but I'm not sure that the statistics of those. What we don't have evidence for is whether there was a fast radio burst. We just didn't have coverage. And we don't know what was happening during the first hours after the event. I've made some predictions that you might get very fast expanding matter, which is composed of free neutrons, and they decay in 15 minutes to protons and could power something very bright in the UV during the first hour. And this event we only got on in the optical 11 hours later, largely because it was over the Indian Ocean and you had to wait for the Earth to rotate so that the telescopes in South America could see it. But in the future, we hope to have a telescope right below the event and get on immediately and see if there's this bright UV event. There are a number of firsts from 170817. It's really striking. This single event was the first time we detected gravitational waves from a binary neutron star merger, the first time we detected an electromagnetic counterpart to a gravitational wave event, and it was seen in radio, ultraviolet, optical, infrared, X-ray, and gamma rays, quite impressive. Is the first definitive connection where I think we have clear evidence that this event made a jet capable of powering a gamma ray burst of the type we see at cosmological distances if we had a slightly more opportune viewing angle. It was the first time people had placed gravitational wave and multi-messenger constraints on the neutron star equation of state. It was the first direct evidence for the creation of the heaviest elements in our universe. And I didn't talk about this either, but you can use the redshift ascertained from the kilonova to measure the luminosity distance and from gravitational waves, and use that with the redshift effectively to measure, to create a Hubble diagram and measure the Hubble constant. And that's something else we could do with more of these kilonova in the future. So with that, I just want to thank all the students and collaborators who have been working with over the years, and for my support from NASA, NSF, Blavatnik Foundation, Steinman Foundation, Breakthrough Prize. Yes. Thank you very much.
Okay, thanks a lot, Brian, for that nice talk. We have time for a few questions.
This is Nick. Can you tell us a little bit about the nucleosynthesis in the Magnestar formation?
In the Magnetar, yeah. Well, yeah. So that's a good question. If you have a long-lived remnant, then it will be, as I mentioned, you'll still have neutrinos from that remnant, even though it's highly magnetized. So, the outflows you still have an accretion disk probably around the magnetar remnant for a period of time, at least before the accretion disk evaporates. But because of all those neutrinos, you're not likely to have enough neutrons left over after this stuff gets out, just to form the heaviest elements. And so I think you would probably from the accretion disk outflows, you probably get the lighter R process elements. Now there's a different source of ejecta, which I didn't have time to discuss, which comes in directly from the neutron star surface. So there's a wind that's ablated from the neutron star surface by neutrinos. And it's normally kind of wimpy if you don't have a strong magnetic field. But if you start spinning a neutron star near breakup and you give it a strong magnetic field, it tends to fling out particles. This sort of it's the same effect that's happens in magnetized stars, not like the sun. The sun isn't rotating fast enough, but there's a centrifugal flinging of material, and so you can get actually significant mass ejection from the magnetar itself during the first few seconds. But it isn't probably coming off. I mean, it's coming off fast, but it's probably still going to form these heavy elements mostly. If you start getting a really ultra relativistic outflow, very high gamma factor, it starts to get harder to make these elements because the fluid elements are expanding so fast that they basically freeze out of the R process, and you don't have time to capture all the neutrons. And so whether the GRB jet, if it's threaded ultimately by a magnetar, is containing these nuclei is quite interesting, because you could imagine, accelerating them to very high energies. If they're in the jet, you could imagine, accelerating them to become ultra high energy cosmic rays or something, which would be pretty cool if you had our process, ultra high energy cosmic rays. That could have an interesting impact on the GZK cutoff, for instance. But anyways, this is quite speculative. So it's probably mostly going to make lighter R process elements, but could be interesting. Yeah.
I have a question. It's very exciting to note that you can determine the radius of the neutron star, at least pin it down to somewhere. But I believe that the calculation that you show for the maximum mass and radius are calculated for non-rotating neutron stars. So presumably in this merging process, the neutron stars are rotating. So how do you account for whether you are comparing apple to apple? Yes.
Yeah. So the mass and radius constraints I was quoting were indeed calculated for non-rotating neutron stars. But then basically you pick an equation of state, and that equation of state predicts a maximum mass and a radius for a non-rotating neutron star. And then you do the simulation with that same equation of state, and you quantify the outcome as a function of those properties of the equation of state. So you're using the maximum mass and radius of a non-rotating star as a sort of proxy for different properties of the equation of state which affect the outcome. So it's taken into account. Now, when I talk about these supramassive neutron stars, the reason that the threshold for collapse is at 1.2 times the maximum is because that extra 20% is because they're rapidly spinning.
Yes.
Okay, so and it isn't exactly, for sake of a cartoon, I've called it 20%, but it can vary between like 18 and 26, depending, or something like that, depending on your equation of state. So it's that. So this is taken into account, I guess, is what I'm saying. But you've described everything in terms of the non-rotating quantities, but ultimately, when you do the outcome, you have to account for. I mean, these thresholds are accounting for the fact that the object is rapidly spinning.
So does that 20% come into play when you say that you can determine the radius to be between 12 or 14?
I didn't describe this in great detail, but it's actually this condition, the prompt collapse, that is sensitive to the radius. So the compactness of the star, which is related to its radius, like m over r, comes into this constraint on the radius. This 20% comes in when we want to put a maximum mass on the TOB mass, because we measure m total and we want to put a limit on m max. And so we basically take it's not quite this simple, but you take the total mass LIGO measures and you divide by 1.2. And that gives you so in other words, the fact that we didn't undergo this third channel, we can say that the m max has to be less than that. The radius comes in through this prompt collapse. I didn't describe this in detail, but there's a nice series of papers by Andreas Bauswein, who go through this method of constraining the radius using the prompt collapse condition. So I'll point you to those papers. Bauswein, 2017. He has some more recent ones too. So
thank you.
Yeah.
Do we have other questions?
Brian, this is Lucas. Thank you so much for a very interesting talk. I know this is not what you focused on, but could you speak briefly to what you would expect from a black hole neutron star merger?
Yeah,
in
sure.
terms of electromagnetic counterpart?
Yeah, happy to.
Thank you.
So as I mentioned very briefly, a black hole neutron star is essentially an all or nothing kind of event. If the black hole is massive and slowly spinning, then then generally it will swallow the neutron star whole. So LIGO had a first black hole neutron star candidate that was like a 25 solar mass, and then there was a lower mass object. They weren't sure it's a neutron star or black hole. That even if that were a neutron star, given that mass ratio and given the low spin of the black hole, it would have eaten the neutron star whole. So we wouldn't expect anything. Although it might produce an FRB from the magnetic field of the neutron star interacting with the black hole before it gets swallowed. So there could still be an FRB from that. But in terms of kilonova and GRBs, we don't expect that from high mass black holes merging with neutron stars. If the black hole mass is smaller, like 5 or 7 solar masses, and particularly if it's spinning rapidly in the orbital plane, then the tidal disruption radius of the neutron star is outside of the horizon, and in that case, half the neutron star, 90% falls into the black hole, and then the outer parts are kind of torn off and make this big disk. They eject some material, they make a disk. So you would expect, a kilonova from the ejected material. You'd expect possibly a GRB from the disk. But the difference is, in that case, there is no central surviving remnant. So you'd expect no neutrino irradiation from the central remnant. You're going to still get some from the disk. But overall, I would expect, because of that lack of neutrino irradiation, that the ejecta would form the heavier elements. And so you'd expect a redder kilonova. So my prediction for black hole neutron star is nothing if it's a massive black hole, or a red kilonova if it's so infrared peaking kilonova if it's a low mass spinning black hole. And this is, again, some bit of information. LIGO has an algorithm that tells you if it's likely to produce one of these disruptions, and I forget, they call it has EM or something, has remnant, I think, or no, that's for the neutrons. Okay. I don't remember.
Yeah, it has some EM flag that allows you to know whether it's worth searching for it or not.
Their previous version of that was very generous. Like, it assumed a 15-kilometer radius neutron star. So even if they had said this one may have a remnant, I still wouldn't believe them until I saw the published paper. So I would expect nothing unless they tell you. But you probably should look anyways. Don't believe theorists.
Thank you.
That's how you win the Nobel Prize. Don't believe theory. No.
Can I ask very generic question?
Yes.
So first of all, it's amazing talk, and I'm amazed that by observing something which happened billions years ago, and only have signal which is many hours after event, you can get some insight in what happened in first milliseconds. That's really fascinating. But basically, all your observables is just color of this neutron star and time dynamics of that, which might have more than one explanation. So I don't really see any smoking gun evidence. So is there any hope that some future observation will give us such smoking gun evidence that that's the hypothesis, that nothing else really can happen?
So you're looking for smoking gun evidence for which aspect? That there was a black hole, or that we form these heavy elements, or?
Well, I would like to have it for everything, of course, but at least for this mechanism of formation, which is now on the screen, that you have mergers and you have some.
The smoking. Okay. Yeah. I think this is a common thing in astronomy. Our data is it's complicated mess. My hope is that. So I gave some sort of qualitative predictions. Okay, more massive binary. Give me something redder, less massive bluer. Okay, if we get that right, then at least we feel like we're on the right track. And the simulations are getting better. We'll hopefully be able to get more fidelity in our predictions. I think ultimately it would be great to detect gravitational waves from the post-merger event, because right now what happens is LIGO doesn't have they have a lot of sensitivity to the in-spiral, but they don't have sensitivity at high frequencies, which is what happens after the merger. So they can't tell you from the gravitational waves alone, did a black hole form? They don't have enough signal to noise. But in the future, with next generation detectors, they're going to, hopefully get more sensitivity at high frequencies, and they will actually be able to measure oscillations of this remnant. I don't know if they'll be able to possibly measure, if there's a remnant, they may be able to see periodicity if there's a surviving remnant for minutes after the event. I think that would be the smoking gun, would be to actually get gravitational waves on both sides of this equation. We're just at the point now where LIGO can tell us what's going in, and then they kind of lose it out of their band, and then we're relying on the electromagnetic signal. So I'm hoping that eventually we will have both. We will have electromagnetic observations that distinguish, find 3 qualitative different types of events. Probably astronomers will call them type 1, type 2, and type 3. And then we'll eventually be able to get gravitational waves and say, oh, okay, that one really did collapse to a black hole. That one really did produce a remnant that survived 100 milliseconds, or that one really did produce a remnant that survived a minute through gravitational waves. So I think that would be, more convincing. And I use the red and blue stuff, but there's an enormous amount of information in the spectrum of these events. And I didn't really have time to talk about it, but we can see individual elements potentially, if we get a nebular spectra after the ejecta has become transparent, with the next generation, like the James Webb Space Telescope, and actually see individual lines from a bunch of these our process elements. I think that would be smoking gun for.
But it seems to be impossible, right? You have so high temperature, Doppler shift will broaden all the lines so that you would not ever see individual lines unless it's cold.
Well, at these times, so it's true, everything starts off really, really hot, but by the time everything is expanded, weeks afterwards, when we're seeing this signal, by that time it's cooled to a few thousand Kelvin, and so the Doppler, it is true, it's expanding at 1/10 the speed of light, so the lines are broadened by that effect. But there may be some bit of material that has a lower velocity, so there may be some narrow core to the lines that would allow us to identify them. It's hopeful. We don't actually know experimentally where most of these transitions are for these atoms. Most of the models for the spectral transitions that I quoted in determining the opacity are based on theoretical models for the atoms, because they're too many to measure in the lab. You need a statistical model. So even if we start seeing, it'll be like the sun again, where when helium was discovered on the sun, people didn't know what it was. They called it mysterium or something, because no one had. And I'm guessing the same thing. We'll see a bunch of lines and we'll be like, what are those? So they don't match any element we know of. So therefore they must come from one of these exotic elements. We'll see.
Okay, thank you. That's very interesting. Yeah.
Okay, I think we're just about out of time. So why don't we give Brian a sort of a virtual round of applause and thank him again for coming and giving such a nice colloquium.
Thank you so much. Appreciate it.
Thank you very much.